The next invited speaker is Rüdiger Haas. Let me start with the formal introduction. Rüdiger Haas is a full professor for space geodesy at Chalmers University of Technology, Sweden. And Rüdiger is responsible for the geodetic VLBI activities at the Onsala Space Observatory. He's also the scientific leader of the Onsala Twin Telescope project. He is the international scene. He is the chair of the European VLBI group for Geodesy and Astrometry, EGVA, and the chair of the directing board of the International VLBI Service for Geodesy and Astrometry, IVS, as well as the member of the directing board of the International Earth Rotation and Reference Systems Service. Personally, Rüdiger and I knew each other for quite a long time. And Rüdiger actually stayed in CRL, Japan, when we were young, in 90s. And I had also an opportunity to stay in Yebes in 2017. So we actually, when we were young, we didn't expect that both of us are being the chair of the IVS and IRS at the same time. And so I feel a bit special. And in his talk titles, the International VLBI Service for Geodesy and Astrometry, Status and Prospects, we will hear a lot of hints for us. I mean, the SLR and VLBI are recognized as a big size space geodetic facilities. Let's look forward to his talk. Thank you very much.
Thank you very much for this nice introduction. As Toshi said, we were sharing office at some time. Quite interesting. So now we'll continue with what Pablo has been introducing already, radio astronomy, or let's say the use of radio astronomy for geodesy and astrometry. And I'm saying something about the IVS, so the brother or sister of the ILRS, working with VLBI. And now I have to find a way to move forward. Other one. Ah, it's backward. Yeah, so as Pablo already introduced, we can use radio astronomy in an interferometric way to make use both for astronomy but also for geodesy. So we look at these objects that are very far away from the Earth. They were created in the birth of the universe, basically, in the childhood of the universe. They're billions of light years away from Earth, and we use them as kind of lighthouses in the universe, like a reference in outer space. And we would, of course, as a geodesist, we always want to have something that is really nicely defined. So we'd like to have a
Rüdiger, sorry, Rüdiger, can you approach the mic a little bit more? I think it's a little bit low.
Okay.
Yeah, thank you.
Can you hear me better now?
Much better, much better.
Yeah. So as a geodesist, you're always interested in to have point-like sources. You would like to have something that is really well defined. So we are interested in the point-like ones. So that's not the ones that the astronomers are interested in. They are, yeah, I see, I have to use my ears. The astronomers want to have something that is interesting from an astronomical or as a physical point of view, but as a geodesist, you're more interested into point-like sources. So there are some that are almost point-like, and we can use them as a reference in outer space, in the universe, and then we can connect the reference frame that is built up by these far distant objects in the universe with the reference frame on the Earth that will be realized then with the telescopes that observe these signals. And we always need partners, so we cannot do VLBI as a single station. Yebes cannot do VLBI by its own. They need partners. They need partners like Onsala, they need partners like Wetzel and so on in order to do it. So we have to have a good relation between these observatories, of course. So the actual observation is this time delay that it takes to receive this plane wavefront. When it has arrived at the Earth, it's a plane wavefront, first at one telescope and then at the other telescope. So this is the true observation that we use and that we finally analyze also to determine all the parameters that are behind it, so that describe the positions of these quasars that we call them, the positions of the radio telescopes on the Earth, but also the orientation of the Earth with respect to the background CRF. So VLBI can do everything, the celestial reference frame, the terrestrial reference frame, and the transformation in between. And another advantage of VLBI and uniqueness is that the only thing that we assume basically is the speed of light. So this is, we are doing a time measurement, we are measuring time delays, we relate them to the speed of light, and we get the scale. So we are good, VLBI is good for the scale. Yeah, there's not only one radio source, of course, but they are distributed all over the sky. This is just to indicate again, we have this background CRF, the celestial reference frame, we have the TRF, which is our telescopes on the surface of the Earth, and then the transformation in between. The celestial reference frame is indicated here, or is shown here. It's called the third version, the ICRF's International Celestial Reference Frame. In the S and X frequency ranges, Pablo already mentioned there are these different frequency ranges that we observe, and the S and X is the legacy, so the traditional geodetic VLBI frequency range in 2 gigahertz and an X band in 8 gigahertz. And these yellow ones are the ones that are kind of used as defining sources for datum definition. Well, they are rather well distributed in the sky. And then we can, as I said, measure the orientation of the Earth with respect to the background CRF, and we can get access to all the components, not only to the polar motion and length of day, but we can get access with VLBI to all components, including the motion of the celestial pole, or the celestial pole offsets, so meaning the rotational axis with respect to the universe, but also the rotational axis with respect to the terrestrial reference frame, polar motion, standard polar motion, and the actual rotational angle, so the difference UT1 minus UTC, which is proportional to the rotational angle. So that's also one of the advantages of VLBI, that it has access to all components of the EUP. And these are, as you know, very much impacted by geodynamic phenomena. So we can see exchange of angular momentum components in the system Earth, like, for example, these El Niño southern oscillations. So when there is lots of masses in the ocean that are moving back and forth in the Pacific area, they show up as variations in the length of day. And we can monitor that nicely with VLBI. So this is a plot here for VLBI observed length of day, and you see these deviations here, these peaks here that correspond to El Niño, large El Niño events. So the IVS as a service, as I said, we need to cooperate with many observatories. It was formed as a service 1999 as a collaborative service of organizations that have to do with, that operate or support VLBI components. And it is actually working as a service for 3 parents. So we are a modern family with 3 parents. We have on the one side, we have the IAG, we have the IAU, and we have also the World Data System of the International Science Council as a parent. We are working as a service for them. And the objective of the IVS is to support geodetic, geophysical, and astrometric research and operations. So to serve both IAG and IAU, to promote research and development, to further develop geodetic and astrometric techniques, VLBI techniques, and to interact with all the users, the community of users that make use of our products, and to integrate it into the global observing system also. It is serving, the IVS is serving the internal group, so to say, so the users internally, but also the community outside. We produce data and products for the scientific community, and our main products are these 3 here. We have a terrestrial reference frame, the VLBI terrestrial reference frame, as the SLR has a satellite laser ranging terrestrial reference frame. We have the celestial reference frame, which only we contribute to, not the other space geodetic techniques, and of course the Earth orientation parameters. So these are the main product groups that we have. As an organization, we are a non-profit organization on a best effort basis, so we depend entirely on our components, that they have funding to do what they do. In total, we have more than 80 permanent components, and they involve network stations, like, for example, Yebes, correlators that do the correlation of the interferometric data. Yebes, I heard recently, was involved or is planning to become a correlator. That's very good. Data centers that have the, save the data that we produce, analysis centers that analyze the data, technology development centers that develop further the technique, like Yebes, for example, operation center that plan, and the coordinating center that organizes and plans. And these 80 permanent components, they are distributed in roughly 40 institutes. Some are institutes that have several of these components. And these institutions, they are both from National Land Survey agencies, space agencies, universities, and pure research institutes. So it's a mix of different institutions that contribute. And they are located in more than 20 countries. In total, they are on the order of 350 associate members in the IVS. The observing plan that we do is both the so-called traditional SX legacy and the new version, the VIGOS. If we look at the SX legacy, that goes back to the early 80s or even late 70s there. We have the first databases from 1979. And they are on the order of 40 stations that contribute to these measurements. It's a large variety of telescopes that is involved. So the smallest one is 6 meters in diameter, the largest one is 100 meters in diameter. It is kind of, these telescopes were often built together with astronomical interests, so they are deformal and slow and astronomical telescopes. Meaning they deform, so we have to have gravitational deformation models for them and so on. So they're not perfect for geodesy in that sense. They're used for 24-hour sessions that we do roughly 3.5 times per week, and 2 sessions of them are dedicated for Earth orientation parameters. So there are session R1, which is on the first day in the week, and R4 on the 4th day in the week. And then there are a number of other dedicated sessions, for example, for terrestrial reference frame, celestial reference frame, and research and development to further develop the system. And then there are, additionally to these longer 24-hour sessions, there are also daily 1-hour short sessions on only one baseline, east-west oriented or west-east oriented, which is very sensitive then for the Earth rotation angles, for this UT1 minus UTC parameter that we're interested in. So we can produce it on a daily basis based from these intensive campaigns. And there are different networks, intensive 1, intensive 2, and intensive 3. The network of stations that are involved in these SX legacy is indicated here. So the red ones are official IVS stations, and then we have the yellow ones which are cooperating SX VLBI stations, and this is mainly the American VLBA, the Very Long Baseline Array, which is an astronomical array originally, but has capability for SX and is cooperating. And you see the majority of the stations are on the northern hemisphere, so we have only a few on the southern hemisphere, so we have kind of an unbalance there, and not all the continents are well equipped with VLBI stations so far. But nevertheless, it's a rather good geometrical distribution. If we look to the new generation or the next generation VLBI system that is called VIGOS nowadays, the VLBI Global Observing System, it started to become or to do observations in 2017, and it's operational since 2020, one can say. Today we have 10 operational VIGOS stations so far, but they also so far only or primarily in the northern hemisphere. And today in 2020 there is 1 session per week. Now we will go back to every second week because we have collected so many data which has to be correlated first, and then we will go back to weekly operations in 2023. And these sessions are used for both or for all the 3, for EOP, for TRF and CRF studies. And then there are also additional, in a similar way as for the legacy ones, there are the shorter 1-hour VIGOS sessions using these new telescopes, VIGOS intensives, and there are several of these sessions every week. If we look at the VIGOS concept here, the idea with VIGOS was to generate the next generation system that is in a way more unique, so to have fast and stiff telescope. Fast telescope meaning they can move very fast from one to the other radio source on the sky, which is important in order to handle atmospheric turbulence effects, so tropospheric parameters in a good way. So the idea is to have very fast 12 degrees per second in azimuth and 6 degrees per second in elevation telescopes, and stiff telescopes that do not deform, so that we do not have problems with gravitational deformation of the instruments itself. And to have broadband capability, to be able to observe in a wide frequency range between 2 and 14 gigahertz in 2 polarizations. The legacy system is in 1 polarization only, the Vigo system is in 2 polarizations. And using these fast telescopes, it should be possible to have at least on the order of 1 observation every 30 seconds, so that you get roughly 6 to 7 times more observations during 24-hour sessions than you get with legacy SX. All the data that are collected should be transferred to the correlators with e-transfer, so electronic over optical fiber if possible. And the expectations from this concept was then that we could get magnitude of improvement compared to the legacy SX observations. And additionally to this concept, there are also 3 sites that are establishing twin telescopes, so where you saw some pictures already from Ny-Ålesund. I will show you a picture from Onsala in a minute. And the idea is there that these can work in different subnets so that we can sample the atmosphere in different directions simultaneously. And that is good for studies or to handle atmospheric turbulence. It also could allow then also to observe VLBI radio sources with one of the telescope, and then these kind of collocation satellites. We heard yesterday about these ideas about collocation satellites with artificial VLBI senders on board of satellites with the other telescopes, so in order to combine with these collocation satellites. So there are a lot of ideas with these twin telescopes. But the network so far looks like this here. We have 10 stations that have been involved in operational sessions so far. We heard just recently from Frank Lemoyne in December there will be Ny-Ålesund, one of the Ny-Ålesund telescopes joining. So then we will have 11. But there is so far only 1 in the southern hemisphere. So we're really waiting for RTB's to be done or to be ready with their Vigo's system so that they can join, and then further telescopes that will be established in South America and in the Pacific area to start with. So one example of these Vigo's telescopes or observatories is the Onsala twin telescopes here, which are 2 identical telescopes, same manufacturer as the one in Yebes, so that you will see later in the afternoon. They are installed at 75-meter distance here, so that they do not block each other too much, but they have a reasonable common atmosphere above. And they are 13.2 meters in diameter, a ring focus design. The surface accuracy is better than 100 micrometers, and they are fast, as I said. We have equipped them with 2 different receivers. We have on the western one, which is this one here, we have a so-called 11 feet, which is covering 2 to 14 gigahertz in 2 polarizations. And on the other one here, we have a so-called quadrich feed, 3 to 15 gigahertz. I think the Yebes one is also a quadrich one. We did so in order to be able to test different kind of approaches and different kind of receivers. And well, it's still in evaluation, and maybe at a later stage we will equip both with the same one. They have phase and cable calibration systems, and they are connected to digital backends, so-called DVC3, 1 each. And these are quite powerful machines. So in the full Vigo setup as we have 8 IF boards. We can cover 16 gigahertz in 2 polarizations, and we can sample basically in 128 gigabit per second if we wanted to. We are not doing it like right now in the Vigo's operations, but this is in principle possible. And we store the data on what we call FlexBuff recorders. So these are dedicated computers with many, many hard disks. And right now we have a petabyte of disk storage available. And then the data are sent from these FlexBuffs to the correlators with fiber via fiber connections. And we have several fiber connections above 10 gigabit per second. So this is one example of these Vigo's sites. So now let's have a look at the Vigo's performance so far. So there have been operational observations with Vigo's since 2019. Before that, there were a number of test sessions, but we can start counting 2019 as a start of operations, 2019, 2020. So we looked at the 3 years of data from 2019 to 2021 and estimated the station positions here. And this is a plot of the station position repeatability, indicated for the different stations and indicating for different components here. And you see the best ones for the horizontal here are on the order of 1.5 millimeter in weighted RMS, and this is the Onsala ones and Yebes. And the best one in the vertical here is one of the Onsala telescopes, which has a weighted RMS of 2.5 millimeters. So this is quite good from these 3 years. If we compare this to simulations, so taking the same observational plan, but simulate data and analyze them, and then compare them to the real observed data, we see on the left-hand side the results from the simulations. So the simulations tell us, well, we should get down to, let's say, 1.2 millimeter for most of the stations in the horizontal component and 3.5 or 3.4 in the vertical. We actually achieve slightly worse. We achieve 2 millimeters in the horizontal and 4 millimeters in the vertical. So we're really close to what we expect from the simulations, which is good. And if we compare that to what is the legacy SX doing right now, so these are sessions that were observed simultaneously both with SX and VGOS. So in these 3 years we had the VGOS sessions always being observing together with R1 or R4. So we could analyze the R1 and R4 legacy sessions and the VGOS sessions independently. Here you should be aware of that the scale is completely different. Here we have 3 centimeters or 30 millimeters from bottom to top, and here it's only 7. So on the right-hand side is VGOS, on the left-hand side is Legacy SX. Legacy SX roughly gets 5 millimeter for the horizontal component, 10 millimeter for the vertical, and VGOS gets roughly a factor of 2.5 better than SS Legacy. So that is really good news. It's very promising. So VGOS is really outperforming SX already today, although we have a rather sparse network and only 10 stations involved so far. If we look at the baseline length, which is always used as a kind of measure to measure how good things are, how good the solutions are, this is the baseline length repeatability. The blue ones are the VGOS sessions, and the red ones, this bulk here, is the SX Legacy. Again, simultaneously observed in these 3 years. And you see, if you take, let's say, 6,000 kilometers, which is kind of a reference baseline that we often use, we see that for VGOS we get the repeatability on the order of 4 millimeters, and for SX Legacy it's more than a factor of 2 worse. So VGOS is actually better than SX Legacy. Again, if we now look to the EUPs, now we have looked at the TRF, basically, station positions. This is now a comparison of Earth orientation parameters. And on the left-hand side, I show you some results from VGOS intensive sessions. So we did a couple of VGOS, so-called VGOS B sessions between Onsala and Ishioka in Japan. And we compared them to simultaneously observed intensive 1 and intensive 2 sessions and different analysis centers and different analysis procedures and so on. And we see that the VGOS ones here get lower values basically in all the columns, whether it's the standard deviation, the mean standard deviation, median standard deviation, the RMS, the bias with respect to reference, and the standard deviation. So from this we see that the UT1, so the Earth rotation angle from VGOS, is already measured better than with SX intensives. And on the right-hand side, this is examples for comparing to an external source from GNSS. And here we focus on the EUPs that can be sensed both with GNSS and VLBI, and these are the polar motion, LOD, and the rates of the polar motion. And here you see the blue bars are corresponding to the discrepancy between VGOS and GNSS, and the red bars, the discrepancy between SX and GNSS. You see for the rotational component, length of day, they are almost the same, slightly worse for SX, slightly worse for VGOS. But for the others, for the polar motion and the polar motion rate, the better distributed SX legacy networks are giving a better agreement to GNSS still. And this is basically showing that the VGOS network configuration is not perfect yet. So here we are still a little bit worse in polar motion, but for UT1, VGOS is already outperforming SX legacy. So then there are, besides these VGOS operational series, there are also research and development sessions, and they are aiming at testing different strategies, doing, for example, very short scan lengths to get as many possible observations as possible, or to test different frequency setups to place the frequencies at different places in order to avoid RFI disturbances and so on. And during 2021 and 2022, the focus was on the short scan length approach, to have as many observations possible as you can. And the minimum and average scan length, for example, for this VR session, VGOS research and development session, was on the order of 7 to 11 seconds only, before switching to another radio source, and then switching to another radio source, and so on. And that gives you very many scans and very many observations. And that allows now, yesterday there was a discussion, or they were mentioning tropospheric effects, and now we are much more affected by the water vapor in the atmosphere than the SLR. So we need to estimate the tropospheric parameters. And now with so many observations that we get, we can do that with a 5-minute temporal resolution. So we have so many observations that we can basically compare us on the 5-minute level with GNSS. And this is what I want to show you now here. So at all the sites that were involved here in these sessions, we have co-located GNSS, often several ones even. And I will focus a little bit more on Onsala, because there we have not only GNSS but also a radiometer, water vapor radiometer, which is a completely independent technique. So it's not a space geodetic technique, but it's a remote sensing technique, basically measuring the sky emission, sky brightness temperatures. And then you can calculate the water vapor amount. So just to give you an example about this increase in number of observations here, here I picked 3 of the sites that are involved, or that are both having SX and VGOS. It's Onsala, Wetzel, and Cookie on Hawaii. And the first row here is for a standard VGOS, standard legacy session, one of these R1 sessions. And there were the average scan length was 75 seconds, and you get roughly 1,600 scans. If you go to a VGOS operational session, which has less number of stations involved, and it has a standard scan length of 30 seconds, you can already increase the number of scans. And you get, for example, here for Onsala, you get an increase by a factor of 2, from 400 scans for Onsala to 800 or 850. And a similar way from Wetzel, for Wetzel and for Cookie. So there's a factor of 1.5 to 2 increase. And if we look at these dedicated research and development sessions that really aim at having very short scan lengths to observe very many observations in the sky, you see that there's another factor of 3. So we get on the order of a factor of 6 more scans per station and better observation geometry. And then we can use them and analyze them. And in Onsala, we have this nice feature that we have, or a nice opportunity that we can compare both two results from GNSS, which is one of the GNSS sites in Onsala, that is IGS station. And we have this water vapor radiometer, which is just a couple of 100 meters away from these, from the GNSS there, and 500 meters away from the twin telescopes. So if we look at that, and now we look at this zenith total delay, so the delay in the atmosphere, both the hydrostatic and the wet part, so it's added up here. Then you see in red the results from VGOS in both sides. So this is compared to GNSS, this is compared to radiometer. So the red line is the same in both plots here. And then in the left side you have the GNSS derived zenith total delay, and on the right hand side you have the radiometer derived zenith total delay, all with the same temporal resolution, 5-minute intervals, no interpolation, no extrapolation, nothing. It's really estimated with the same temporal resolution. Then you see the differences here. Here you see the correlation plot. Correlations are 0.98 in this case, 0.95, so well above 0.9, very highly correlated. And this is kind of a distribution or differences as a function of absolute value. So we get very high correlated zenith-total delays. We also have gradients, so the horizontal change, which is expressing the inhomogeneity in the troposphere. And again, here the red one is from Vigos, from the Vigos telescope. The blue one on the left side is from GNSS for the north gradient, on the east side for the east gradient. And here the correlations are 0.3 and 0.84. So also higher correlated for the east gradient than for the north gradient in this case, which makes sense for Onsala because we usually have westerly winds, so the water vapor comes from the sea and goes into the inland, so we get a more of a gradient towards the east. And this is the comparison to the radiometer here. Again, the red curve is the same as before on the slide before, and the blue is now from the radiometer, and here we get also correlations that are 0.5 and 0.76, so also high correlated, and the east gradient is higher correlated than the north gradient. So this is a very good indication that Vigos is really able to sense these tropospheric variations, so this turbulence in the atmosphere, and that we shouldn't be estimating gradients for a day or half a day or something, but we should really go down to short intervals, and it's verified by completely independent techniques like the radiometer here that it's not nonsense, but it's really a signal that we can sense there. Then let's have a look at radio sources. Pablo mentioned the radio sources, and we are not really seeing the black holes, although they are these active galactic nuclei, but we're not really seeing them, but we're seeing somehow the jets that are coming out of them. And the position of this radiation can be at different positions also, and that can appear as kind of a structure of the radio source. And this is an example here for these 4 Vigos bands that we're observing now, around 3.3 gigahertz, 5.5, 6.6, and 10.5, which is a standard setup right now. And this has been used now to make an image of a radio source at these frequency ranges. And the scale here is the same. It's plus minus 3 milliarc seconds. And this is in right ascension, and this is in declination. And you see that in the lower frequency range, it's more extended, and then it becomes more and more compact. So we see more and more, we zoom in with our instruments. We have a zooming device, so to say, and we see the compact part of the radio source more and more clearly. So that is very nice. That is, so we didn't see these things with SX. We were blind at that, but now we have the ability to observe over the whole wide frequency range between 2 and 14 gigahertz, and can make images of these sources at different frequencies and really identify the point-like structures in these sources. So that's a very good feature with Vigos. We can do broadband imaging of radio sources. And we can also, and this is something that we've done with our short baseline, just 2 telescopes, 75 meters at Onsala, we can monitor the flux, so basically the signal strength of the radio sources. So during the summer last year, we made a short experiment here. We had 91 sessions, half-hour sessions, where we observed a number of radio sources, and then we correlated the data, analyzed them with an astronomical software package, and determined the flux density in Jansky. And this source here that I show you here, the 0059 plus 581, this is one of the sources that is often observed in VLBI, both in the SX but also in Vigos. And you see during these 91 sessions, it's a little bit more than 2 months here, we had a vacation time here, it was flaring. So it had some areas where it has a very high signal, very high flux density, and then it was decaying in flux density, so it's variable over time. And the signal strength, or this flux density of a radio source, is a very important ingredient to plan VLBI observations. Now, if you do the planning of a VLBI observation, you need to calculate how long do I need to observe this radio source. And this depends on how sensitive your instruments are, but also how strong the signal is in the sky. So if you have good information about the actual flux density with low latency, you can make better planning of VLBI observations. So if you start assuming that the radio source has this flux density, but actually it doesn't, and your calculations for the time that you observe are based on this flux density, you will probably be not able to detect it at all. So it's very important to have correct information about the signal of our radio sources in good time and with low latency. And that can be done, for example, with twin telescopes easily on a regular basis. Okay, so to summarize, IVS currently rolls out a fantastic and very powerful new observing system that we call VIGOS. It outperforms the SX legacy already today in terms of station positions, on baseline repeatabilities, and the UT1 minus UTC on these long baselines. We're still a little bit weak on polar motion compared to SX legacy because we're missing long north-south baselines in the network, so the network geometry is not optimum yet. We have, with these many observations that we can do, a nice tool now to address atmospheric, tropospheric turbulence effects, which will improve also then the VIGOS operations and analysis. We can also routinely use our data to make images of these radio sources that we observe, and almost in real time do flux monitoring of radio sources using these twin telescopes. And there will be at least 2 more twin telescopes operational. Right now it's only Onsala that's operational, but Wetzel and Ny-Ålesund eventually also will become operational twin telescopes. So then we can do that at different places and coordinate that also. And in the future, let's say 5 to 10 years from now, I hope that the VIGOS network will look like this here. We will have stations in Australia, so they are doing a conversion now from SX to VIGOS. The first one that is already converted is Hobart, but there are 2 others that will be converted soon. Hartebeestuk will hopefully become operational at some point. There are plans for telescopes in Brazil and in Argentina, in the Pacific area. Probably have missed some here in the Southern Hemisphere. And there are many others to come in Europe, Metzehowe, Ny-Ålesund, all the Reche telescopes in Italy and so on. So in, let's say, 5 to 10 years, we will have a network of stations that is good enough to do to produce all of our products, even the polar motion products, with the high accuracy that we want. And so the outlook is then that VIGOS will basically take over from SX. It will become the workhorse of the IVS. We will use VIGOS for all our products, CRF, EUP, and TRF. We will also need in the future some level of SX, because we want to continue the CRF, so the celestial reference frame, and exploit it or expand it into a multi-frequency celestial reference frame, so to build up both SX but also for the VIGOS frequencies. To do all of this, we need roughly 40 globally distributed VIGOS stations. We need to keep at least 30 globally distributed SX stations also in order to do the CRF work. And of course, we need a number of correlators to correlate all the data, which is still a problem. So far, there are not so many correlators, and we are having a backlog right now of recorded data that needs to be correlated first. The plan is in the future then to have at least these intensive kind of measurements for the UT1-C twice a day, and to produce UT1-C with low latency, so to have this fast process correlating and analyzing the data, and then to have additionally 24-hour sessions with many stations, a bigger network for EUP and TRF, and then for both VIGOS sessions and SX sessions for CRF, also a couple of sessions per year. And then, of course, one is always interested in developing further and having some research and development sessions mixed in there. So the challenges are, of course, we are, as I said in the beginning, a non-profit and best effort organization. We do not have money. It's only the institutions that have money, or they have to search for money, like Pablo explained to us. We also realize it takes time to build new VIGOS stations. It's expensive and takes time. It's a little bit slower than expected, the rollout. But there will be many stations in the upcoming 2 to 5 years that will be operational. And some of the stations still need to be upgraded. Some of the existing stations need to be upgraded to full VIGOS specifications to, for example, reach the highest frequency bands and to do the high gigabit sampling that we planned from the beginning. Then, as Pablo mentioned, there's of course a potential risk that we have problems with RFI, so radio frequency interference in the VGOS bands, for example, by 5th generation mobile phone, Starlink, and so on. And currently there are some initiatives to get some kind of protection for these frequency ranges on different levels in the International Astronomical Union, on the IUGG level. We'll see how this works out, whether we'll be successful to fight the commercial interests. I'm a little bit skeptical there, but we can give it a try at least. And another challenge is, of course, that we produce huge amount of raw data. So currently, with the current system, we have per station, so per telescope, 25 terabyte per day, roughly. If we go to the full VGOS plan, as initially planned, we will have at least 50 terabyte per day. And these data need to be shipped to the correlator, and we do that over optical fibers, and the correlators need to be able to accept 50 terabyte or 25 today from the stations and from 10 stations, so they have to have big pipes into the correlator, and there's some kind of a bottleneck problem right now. So it takes time to get the data into the correlator, and it takes time to correlate the data. So the turnaround time right now is on the order of several months, so it's 3 to 4 months before we get results from our 24-hour sessions. So this is something that we need to solve, and we need also more correlators to be involved. So I'm very happy that Pablo wants to build a correlator. Where is he sitting? Oh, there you're sitting. That's very good news, that we will have a correlator in Yebes. Okay, I think that is everything that I have to show. Thank you very much.
Thank you so much, Rüdiger, for such a great introduction about IVS. We have already got 2 questions online. Let me start with Frank Lemoyne's. Rüdiger, what is the cost for the WVR water vapor radiometer that you installed at Onsala? And would you recommend that some core sites can be equipped with WVR? Second question, how do you calibrate the radiometer?
The first question, we're just in the process of buying a new one, and that is on the order of 150,000 euros, something like that. The one that I showed you is a home-built one, so this you cannot buy anywhere, but there are companies that produce them, and I think it was on the order of 150,000 euros. The second question I didn't really get.
How to calibrate it?
How to calibrate?
Yeah,
they are calibrated using liquid nitrogen, so you can do calibration with liquid nitrogen. So you measure the emissions with a reference source, so to say, and then you calibrate the radiometer. You have to do it on a regular basis, of course. Like you have to calibrate your barometers, you have to calibrate your radiometers also.
Okay, thank you. The second question, a different person, Stefan Liepel. Isn't the Starlink constellation a threat to the VGOS broadband receivers?
A threat?
Starlink.
Yeah.
Will be the threat for you?
Yes, it is. Right now, Starlink has excluded, if you look at their coverage maps, they have excluded areas around radio telescopes, but I'm not sure that this will be valid for all time, or it has to probably be renewed. So, yes, it is a problem, it is a potential threat that they will use frequency ranges and we will be blind in that range, yes.
Thank you very much. Yeah, go ahead.
Have you noticed any difference in scale between VGOS and SX?
Scale, you mean you're referring to the TRF scale now, I guess?
Yes.
We haven't seen anything like that, no. We have in the process for producing the ITRF 2020, we have submitted solutions with and without VGOS, including the VGOS, not including the VGOS. You're referring to this strange scale behavior after 2013.75. It didn't make a difference. So we cannot pinpoint it to VGOS, unfortunately. Or fortunately, maybe.
Well, you can't put it on.
We have some other suspects. We have some other suspects, but not VGOS. Yeah.
Thank you. One more. Go ahead. Just a moment. Microphone is coming.
NAVIC satellites, so the satellites of the Indian satellite navigation system, are broadcast signals not only in the L band but also in the S band. Would it be possible for the VLBI stations to track these satellites?
Yes, it should be possible. We haven't tried yet so far. We tried L-band observations with to GNSS, but we haven't looked at S-band. With the standard SX system, yes, it should be possible.
Okay.
Maybe we should discuss which satellites you're talking about.
The NAVIC satellites, so this is the Indian navigation satellite system.
Okay. Yeah, I didn't know that. Okay. Yeah, should be possible.
Okay, thank you.
Thank you. Any other questions from the audience? You? Okay.
In the SLR community, we have this problem of how to correctly acknowledging the efforts of SLR tracking stations, because you don't get to publish much by just tracking. I wonder if the IBS, you face the same problem and you have cracked it.
It's very difficult to hear, once again.
Yeah, so I wonder if at IBS you have the same problem that we have the SLR community, where it is difficult to acknowledge the efforts of tracking stations and observatories.
Yeah. That's a common problem, yes. We haven't really solved that yet. To give really credit to the people at the stations doing the work, yes. But we have to address it at some point. Maybe we can learn from you. I don't know.
Okay, let me conclude this session by saying thank you, applauding to the speakers.